Hello all, welcome to Operations Research course. We are talking about formulation, how to model integer programming formulations, and in this lecture we are going to solve a machine scheduling problem. We are going to formulate a machine scheduling problem. So let's get started. Okay, so in this example we are going to formulate a machine scheduling problem. In this problem we are given 5 jobs, and these jobs must be processed on a single machine. Assume that this is our machine. So there are jobs 1, 2, 3, 4, 5, and these jobs will be loaded on the machine one by one, and they will be processed, and after that the next one will be loaded. And the processing time of the jobs on the machines is not important to us for this example, but what is important is this. When a job is completed, before the next one can be loaded on the machine must be set up. And this setup time depends on the processing time. So let's assume that if the first job is being processed in the first place, and when it is completed, the next job will be loaded, which is job 2. Let's assume that. Okay, so if after job 1 we load job 2 onto the machine, the required setup time is 10 minutes. But if instead of 2, if we load job 3 to the machine, the required setup time is 2 minutes, okay? So the setup time depends on the sequence. And the problem is to determine the sequence of these jobs so that the total setup time is minimized. So what do we mean? Let me give you an example. If the ordering of the jobs is like this, we first process job 1, this is our machine, then we process job 3, then 5, then 4, then 2. Okay, so between 1 and 3, the required setup time is 2 units. Between 3 and 5, I mean if 5 follows 3, the required setup time is 1 unit. Between 5 and 4, the required setup time is 9 units, and between 4 and 2, the required setup time is 6 units. So the total setup time of this sequence is 18 minutes, okay? And we want to find the ordering which minimizes this total time. Okay, now if you understood the problem, it is time for you to think about how we can formulate this. So please pause the video now and try to first write the decision variable, and then try to write our objective function and constraints for this problem. Okay, I hope that you worked on the problem. You thought about this problem a little bit. Let's formulate it all together. Okay, what are we trying to decide on? When I ask this question, sometimes the students answer that we try to decide on the minimum setup time. No, we are not trying to decide on minimum setup time. We are trying to decide on something else. As a result of this decision, the setup time is minimized. So what actually we are trying to decide on? It is the ordering of the job, okay? Ordering of the job. What do we mean? So the ordering can be 1, 3, 4, 5, 2, or it can be 2, 5, 1, 3, 4. So somehow I need to represent this ordering. I need to find this ordering. How can I identify that ordering? Actually, there are different ways to do it, but in this one, I will show you only one alternative. And look, we are trying to find the order of 5 jobs. It means that these 5 jobs will be placed in 5 positions. So we will have position 1, position 2, 3, 4, and 5. Okay, and to each of these positions, I am going to assign one of these jobs. Let me write job A, B, C, D, and E. So these are the 5 jobs. So for example, I can place job A to position 3, job B to position 1, and then job C to 4, D to 2, and E to 5. So when I do this, it means that B is in the first order, first position, D is in the second, and etc. So simply I'm trying to find this. If I assign each one of these jobs to one of these positions, I find the ordering. Okay. So I am going to define my decision variable in this way, and I would say that let xji again be a binary decision variable. Again, look what we are doing. We are assigning the jobs to positions. It is similar to, again, the definition of the decision variable is similar to the assignment problem. Okay, so what do I say? It takes the value of 1 if job J is assigned to position I, and it is 0 otherwise. And the thing is, how many jobs do we have? It is 1 up to 5. And how many positions do we have? For each one of the jobs, we have a position. So number of positions is also 5. Okay, now I will start with formulating this decision variable, and if necessary, I would include additional decision variables. I don't know at this point if I need or not. So let's try to write the objective function, and the objective function is to minimize the total setup time. Okay, now I need to be able to write the setup time. If the order is like this, BD, I mean here, in order not to confuse you, I represented the jobs as BD and etc., but actually the jobs are also numbered. So let me write it here. Let's say it is 2, 4, then I don't know, maybe 5, 3, and 1. Okay, so after, I mean, if this is the order, then the setup time is, since job 4 follows job 2, the setup time will be 5 units. So in the objective function, somehow I need to be able to write this. But how? Using this decision variable. So here, if job 2 is in position 1, so x21 means job 2 in position 1. And if job 4 is in position 2, x42 is job 4 in position 2, then the setup time will be 5. So what can I do? I can multiply this. If this is equal to 1 and this is equal to 1, then 5 times this, it will incur such a setup time. But there are two difficulties associated with this one. The first one is, okay, job 2 and 4 can be first two positions, or they can be in the second and third positions, or they can be in third and fourth positions, and in all of them, I would have a setup time of 5 units. So it means that this second one, it is not only for 1 and 2, it can be 2 and 3, it can be 3 and 4, and in each one of them, I would have a 5 units of setup time. So if both of them are equal to 1, then this 5 units of setup time will incur. So I need to write for this all of them. But the second problem here is I am multiplying two decision variables. Okay, this is the multiplication of two decision variables, and I need to linearize it later on. And since both decision variables are binary, yes, I can linearize them. Okay, so this way of thinking is okay. First you write it in this way and then linearize it. Never leave these kind of multiplications in your model, always linearize them. But instead of this one, I'm going to use another alternative, and for this I would define another decision variable. And I will say that for this decision variable, it will be yjk this time. It will take the value of 1 if job j is processed immediately before, if job j is scheduled just before job k. So j and k both now indicates jobs, and j goes from 1 to 5 and k goes from 1 up to 5. Now I have two decision variables, and I'm going to write the objective function using the second one because it will be easy. For example, if y12 is equal to 1, what does it mean? It means that job 1 is processed before job 2, or job 2 follows job 1, then the setup time is 10 units. So what I'm going to do is I'm going to write this. Of course, 1 cannot follow 1, therefore here j cannot be equal to k. We can write as a condition. And what we try to do, we try to minimize 10 times y12 plus 2 times y13 plus 5 times y14 plus 8 times y15. So I'm multiplying each one of these setup times with the decision variables, and the last one will be 9 times y54. And I'm multiplying with the setup times and with the associated variables, so that if this is 1, then the setup time is 10. If this is 1, then the setup time is 9. So if job 4 follows job 5, then the setup time will be 4 units. And of course, we need to write this in compact form. And in order to write this in compact form, I'm going to define these setup times. This was y14. These setup times as a parameter, and I'm going to represent the setup times with this parameter as, let me write here, as jk. And this is the setup time if job j is followed by job k. So I'm not saying this is a binary parameter. Okay, it is not binary. It is the setup time. So what does it mean? It means that, for example, let me give you some examples. This is S12. S12 is 10 units. This is S23. If 3 follows 2, then the setup time is 11. Okay, and now in my objective function here, in order to write it in compact form, simply I will multiply this sjk with yjk, and I will take the summation over j from 1 to 5 and k from 1 to 5, and also, if you like, you can add j is not equal to k over here. Okay, so this is the total setup time that we are minimizing, and the constraints. Now, what are the constraints? Look, first of all, this assignment, can a job, for example, job 1, can it be followed by job 2 and job 3 at the same time? This is not possible, right? So each job must be followed by only one other job. We define this xji to be assigned to position. I'm changing my wording. Can this job 1 be assigned to position 2 and 3 at the same time? No, it cannot, right? It can only be assigned to only one of the positions. So it means that this job 1 can either be assigned to position 1 or position 2 or position 5. It cannot be assigned to more than one positions. Similarly, job 2, job 3, each job must be assigned to only one position. And how do we write this? We say that this xji, summation I from 1 to 5, should be equal to 1 for each job, they can only be assigned to a single position. Okay, and this is very similar to the assignment problem formulation. Another constraint, let me write in this way. Another constraint that we have is this. I'm going to continue on this side. Consider position 1 for this time. Can we assign to this position 1? Can we assign job 1 and job 3 and job 4 at the same time? No, this is not possible. For each position, I need to assign just a single job, right? So considering position 1, x1, 1, x2, 1, up to x5, 1. These represents if these jobs are assigned to position 1 or not, and this summation will be equal to 1. So the compact form of this one will be j from 1 to 5 x and j I should be equal to 1 for each position this time. And also this is also very similar to the assignment problem. Until now the formulation is exactly the same as the assignment problem, these two constraints. Okay, each if you consider the assignment problem in which we are assigning jobs to workers, each job must be assigned to one worker and each worker can handle only one job. Exactly the same formulation. But the objective function is different because we are using a different decision variable in the objective function. Now, if you just write this model in Cplex and solve in this version, you would get the objective function value to be 0 and all yjk values will be 0. Why is that so? Because this yjk does not appear in the constraints, and all yjk, since we are trying to minimize, all yjk will be equal to 0. But what does yjk indicate? It indicates if a job k follows job j or not, because if job k follows job j, then there will be a setup time which is represented by sjk. Okay, so it means that there is a relation between x variables and the y variables. And what is that relation? Let me try to explain it here. Assume that x, for example, 2, 1 is equal to 1 and x 4, 2 is equal to 1. What does it mean? Job 2 is assigned to first position. So this is job 2. And job 4 is assigned to the second position, which is this one. So from here we understand that these are on adjacent positions and job 4 follows job 2. So in this case, what we should have is y24 must be equal to 1. Job 4 follows job 2. So if this is 1 and if this is 1, then job 24 must be equal to 1. But similarly, not only for this case, but also for this case, if job, let's say, 2, 3 is 1 and 4, 4 is 1, now this is position, this is position 3 and this is position 4, but still job 4 follows job 2. So again, for this case also y24 should be equal to 1. So how can I write it? I would say that y24 is equal to 1 if x2 is assigned to a position I and x4 is assigned to position I plus 1. Okay, so if they are adjacent, this is position I and this is position I plus 1, this is 2 and 4, then this should be equal to 1. So in order to write this as a constraint, what do? I say that this should be greater than or equal to this summation. But of course this summation, if this is 1 and if this is 1, it will be 2, and this is binary, it can never be 2. So in order to adjust it and write the correct formulation, I simply subtract 1 from this right hand side. And by this formula, I understand that job 4 follows job 2. But of course, I need to write this for all combinations of the jobs. Job 1, job 2 follows job 1, job 3 follows job 1, all combinations. So it means that I need to write it in a compact form, and the compact form will be like this. Yjk greater than or equal to this j, okay, yjk means k follows j. So this j will be assigned to position I. Now let me write it here. This is position I and this is position I plus 1. A job is assigned to here and k is assigned to the next one. In that case, this yjk will be equal to 1. So xji plus xji plus 1 minus 1. This minus 1 is important, otherwise it will be wrong and infeasible. And now I'm going to write this constraint for all j and k, for all jobs. But j is not equal to k. I will not write this constraint for the same jobs. And also be careful, pay attention to this. I need to write this for all I, for all positions. From 1 up to, if you write 1 up to 5, look what will happen. If you put value of 5 here, it will be 5 plus 1, 6. And it is not possible. There is no sixth position. There are only 5 positions. So it means that the maximum value for I should be 1 less than the number of positions. It means that it is for, because of this I plus 1 over here. So the constraint, the final version of the constraint that I should write is this one. Yjk greater than or equal to xji plus 1 minus 1. It is written for all j and k, for all job pairs and for all positions. And of course, the non-negativity and sign restrictions says that xji and yjk are all binary decision variables for all j, I, and k. Okay, so this is the final formulation for this problem, which minimizes the total setup time, which allocates each job to one position and only one job to each position, and also identifies which job is followed by which other. Okay, so this was a simple, this was an example of a machine scheduling problem and how we formulate it.